Hey my dear data friends, it's Nicola from Data Mozart. Welcome to a brand new series of videos which is called Fundamentals of Data Modeling. So in the next 5 weeks, I'll introduce to the basic and fundamental concepts of data modeling in general. So this is not specifically related to any tool or any technology, it's about data modeling in general. So we'll examine different approaches to data modeling. You'll understand basic differences between different data modeling techniques and concepts, and then afterwards we will learn how to implement some of those concepts and techniques using a specific tool. In our case, that's going to be a Power BI, and maybe we will touch upon also Microsoft Fabric. So in this first video today, I want to introduce to a general concept of data structures and to a concept called OLTP, which is an abbreviation for online transactional processing. So stay tuned, and looking forward to hear your thoughts in the comments about this series of videos. Let's first try to define the data. And when I say try, I really mean it, as there are hundreds of different definitions. Data is a collection of facts such as numbers, words, measurements, or just a description of things. I know that this probably sounds too abstract, so let's try to make it more convenient with a practical example. This is my dog Paco. Hi Paco. He's white and brown and he has short hair. He has 4 legs and weighs approximately 8.4 kilos. He's also 42 centimeters tall and, believe it or not, eats almost 5 kilos of dog food per month. Now, why should you even care about Paco and how much he can eat? Well, let me reiterate once more the sentences I've just told. Paco is white and brown, is short-haired, has 4 legs, weighs 8.4 kilos and eats approximately 5 kilos per month. When I say that Paco is white and brown, I shared some qualitative data about him. On the other hand, facts about his number of legs, his weight, and the amount of food he consumes are examples of quantitative data. Additionally, Paco's number of legs is a discrete type of quantitative data. Discrete data can only take certain whole number values. Weight and amount of food represent a continuous type of quantitative data. That means that the data can take any value within the range. Again, you've got a more detailed overview of Paco's data. Still, why that should be important for you? Well, let's say that you are running a pet shop business. By being able to understand various types of data, you can leverage that knowledge and discover multiple important insights. For example, how many customers do you have? Or which dog types are the most popular? You can also find out average eating habits of the pets, and based on that knowledge, you can properly plan a procurement or find additional methods to improve your services. And this brings us to a key takeaway. Data helps you make better decisions. When I say better decisions, I mean informed decisions. Decisions that are based on the knowledge coming from the data. Now that you know what data is, you need to understand different types of data sources. As you can assume, data is everywhere around. It comes from various devices such as mobile phones, sensors, or IoT devices. Data can also come from different databases, both relational and non-relational. Different files could also store data in different formats, for example JSON files, XML, or CSV files. Moreover, video and audio files are also considered as a source of data. As you may notice, data comes from diverse sources, and different types of data require different types of storage. That means you can't store, let's say, video and JSON files in the same manner. Let's first take a look at structured data. Most often, structured data comes in some kind of tabular form, and that form is represented by rows and columns. The next thing to keep in mind is that there is a relationship between rows and columns. Finally, structured data depends on the data model existence. This model specifies how data can be stored, processed, and accessed. Typical examples of the structured data sources are relational databases and Excel files. Non-structured data, on the contrary, doesn't have a predefined model, or it's not structured in a predefined manner. Requirements to store and process non-structured data had largely grown in recent years, especially in the context of big data. Common examples of non-structured data are audio files, video files, and NoSQL databases. Somewhere in between structured and non-structured data, we can place semi-structured data sources. This data doesn't come with a predefined model, but still relies on some kind of structure. And this is a self-describing structure. It contains tags or other marker types that make separation of semantic elements possible, while also enforcing establishing hierarchies of values and fields within the data. Typical examples of semi-structured data are XML or JSON files. In this example, you can see two JSON documents containing data about the customer. In both cases, documents include child elements about name and address, but the fields in these child elements are different between the customers. One of the key purposes of a relational database is to ease the process of storing data and enable quick data retrieval. A relational database provides an established model for data storage and query capabilities to get your data back quickly. When you are building a relational data model, you first need to define entities. An entity is a real-world object of interest, about which the information needs to be stored. Entities in the model are linked between themselves, and these relationships between the entities are the second building block of the relational data model. You already learned that entities represent objects of interest, and those objects are modeled in the form of tables. Essentially, tables are being referred to as a collection of entities from the real world. These entities can be products, customers, sales, and so on. A table consists of rows and columns. Each row represents a single instance of the entity. For example, in the products table, each row contains data about a single product. Each row in the customers table holds data about a single customer, and so on. Column specifies various properties of the entity, such as product description, product category, or customer address, phone number, or customer name. Some table columns are different than the others. Those columns are responsible for maintaining relationships within the data model. Let's examine a basic example of the relational data model. Customer ID column in customer table uniquely identifies each row of the table. When a column or set of columns uniquely identifies a row in a table, this column is being referred to as a primary key of the table. Every table should have a primary key. Same applies to the product ID column within the product table. Now, our order table contains both customer ID and product ID columns. The customer ID column refers to the customer table, so we can identify the customer that placed the order, while the product ID column relates to a product table, enabling us to find out what product was purchased. Customer ID and product ID columns in order table are being referred to as foreign keys. They relate to primary key columns from other tables and are used to establish relationships between the tables in the data model. Let's now reiterate through the key characteristics of a relational database. All data is in tabular form. Tables represent real-world objects. Each instance of the object is a row in a table, while columns store information about each property of the object. All rows in one table have the same set of columns. One entity can contain any number of instances. In other words, a table can contain any number of rows. A row in the table is uniquely identified by primary key. Foreign key is used to reference rows in the related table. For each foreign key value, there should be a corresponding primary key value in the other table. One of the key differences between relational and non-relational databases is their purpose. Relational databases are suitable to handle transaction processing in the most effective way. Let's stop here for a moment and define what transaction means in terms of database workloads. The transactional database must provide an acid set of rules to ensure that the database state remains consistent during the transaction processing. Let's examine what each of the letters in this acronym represents. A stands for atomicity. This concept ensures that each transaction is considered as a single unit, and this unit can either be completely successful or completely unsuccessful. Simply said, if one of the statements within the transaction fails, the whole transaction fails. C stands for consistency. Imagine the transaction of transferring money from one account to another. In this transaction, when you add funds to one account, there must also exist a corresponding deduction from the other account. Consistency, in this case, means that the transaction takes data from one valid state to another. I stands for isolation. This concept ensures that the database will be in the same state when multiple transactions are being executed concurrently, as if they were executed in sequence. D stands for durability, which means once a transaction was committed to a database, it remains committed even if the whole system fails afterward. Online transaction processing systems are suitable for processing a high volume of transactions. When I say high volume, I mean millions of transactions per day. As the emphasis in the OLTP system is on fast processing, tables are normalized to a third normal form to support quick and efficient insert, update, and delete statements. Online transaction processing systems are convenient for running simple ad hoc queries. Since OLTP databases are being updated frequently, sometimes transactions may fail in the middle of processing. Therefore, preserving data integrity is one of the crucial tasks in OLTP systems. In theory, you can model almost any kind of data as a collection of tables with a predefined set of columns and establish relationships between them. However, there are certain use cases when OLTP system implementation makes more sense than other architectural solutions. Common examples of online transaction processing systems that rely on relational databases are banking solutions, flight reservation systems, and various e-commerce applications. That's all for this week. In order to stay up to date and follow along this series of data modeling videos, make sure to subscribe to Data Mozart channel down below. Also, if you like this video, please make sure to click this like button down below. And see you next Friday.